Today we discuss the history of electronics. Electronics has different meanings to different people and in different countries. We will define the term electronics in the sense used here. Electronics is the science and technology of the passage of charged particles in a gas, in a vacuum, or in a semiconductor. Particle motion confined within a metal only is not considered electronics. Electronics is the science and technology of the passage of charged particles in a gas, in a vacuum, or in a semiconductor. Particle motion confined within a metal is not considered electronics. Before electronic engineering came into existence, electrical engineering already flourished. Electrical engineering is the field which deals with devices that depend solely on the motion of electrons in metals. For example, a generator, a motor, a light bulb, or a telephone. The principal benefactors of these devices are the wire telephone or telegraph companies and the power industries. Both electronic and electrical engineering owe their existence to the pioneering work in electricity and magnetism of scientific giants such as Coulomb, Ampere, Ohm, Gauss, Faraday, Henry, and Maxwell. Maxwell, in about 1865, put together the researches of the others into a consistent theory of electromagnetism, now called Maxwell's equations. Here is a historical example of theory being ahead of experiment. For although Maxwell's theory predicted that electromagnetic waves could be propagated in space and that light was such an electromagnetic wave, it was not until 23 years later, in 1888, that Hertz produced such radiation using a spark gap oscillator. In 1896, Marconi succeeded in transmitting Hertzian waves and detecting them at a distance of about 2 miles. Wireless telegraphy had its feeble origin in this experiment. The history is divided into two periods of time, referred to simply as the past and present. By past is meant the era of the tube, the vacuum tube, or the gas tube. The present starts with the invention of the transistors in 1948. Also included is a section speculating briefly on the future. The past. The beginning of electronics came in 1895 when H. A. Lorentz postulated the existence of discrete charges called electrons. 2 years later, J. J. Thomson found these electrons experimentally. In the same year, 1897, Braun built what was probably the first electron tube, essentially a primitive cathode ray tube. Discovery of vacuum tubes. It was not until the start of the 20th century that electronics began to take technological shape. In 1904, Fleming invented the diode, which he called a wall. It consisted of a heated wire which emitted electrons, separated a short distance from a plate in a vacuum. For a positive voltage applied to the plate, electrons were collected, whereas for a negative potential, current was reduced to zero. This valve was used as a detector of wireless signals. 2 years later, Picard tried a silicon crystal with a cat's whisker, a pointed wire pressed into silicon, as a detector. This was the first semiconductor diode. This device was very unreliable, was soon abandoned, and semiconductor electronics died a premature death in 1906. The most important milestone in this early history of electronics came in the same year 1906 when De Forest put a third electrode, a grid, into the Fleming valve and thus invented the tube, which he called an ODR. A small change in grid voltage resulted in large plate voltage change. Hence, the ODR was the first amplifier. It took about 5 years to improve the vacuum in the ODR and to add an efficient oxide-coated cathode in order to obtain a reliable electronic device. Thus, the age of practical electronics began in about 1911. Radio and television. The first application of electronics was to radio, and simultaneously with the birth of electronics, the Indian Institute of Radio Engineers (IRE) was founded in the United States in 1912. It's a great tribute to the imagination of the early engineers that they realized immediately the importance of radio and formed this organization at the very beginning of radio communications. The American Institute of Electrical Engineers, which took care of the interests of conventional electrical engineers, had already been founded in 1884. Both societies combined in 1863 to become the IEEE, the Institute of Electrical and Electronic Engineers. The first radio broadcasting station, KDKA, was built in 1920 by Westinghouse Electric Corporation in Pittsburgh, Pennsylvania. By 1924, just 4 years later, there were 500 radio stations in the United States. The history of broadcasting, both radio and TV communications, can be divided into three periods. 1907 to 1927. The devices available were simply diodes and triodes with filamentary type cathodes. The circuits that were invented by the ingenuity of the engineers were cascaded amplifiers, regenerative amplifiers, Armstrong in 1912, oscillators, heterodyny, Armstrong in 1917, and neutralization to prevent undesired oscillation amplifiers. 1927 to 1936. The indirectly heated cathode was invented for the diode and triode. Two additional electrodes, a fourth and then a fifth, were introduced into the triode to form the screen grid tube and the pentode respectively. Also, beam power tubes and metal tubes were introduced during this period. With these new devices, engineers were able to invent the super heterodyne receiver, automatic gain control, single knob tuning, and multi-band operation. Radio was a flourishing business. 1936 to 1960. In this last period, the new devices were closely spaced electrodes for a high gain bandwidth product, miniature glass tubes, and towards the end of the period, color television tubes. Major Armstrong in 1933 invented frequency modulation. About 5 years later, the first FM receiver was available. Electronic black and white television began in about 1930. The most important name here is Zworykin of RCA. 10 years later, television, at least in the United States, was in fair use. Commercial color television began around 1950, and many new functions had to be performed. Hence, the following circuits were invented: FM limiter, FM discriminator, automatic frequency control AFC, sawtooth waveform generator, linear reflection for a TV tube, synchronization, multiplexing, and inverse feedback circuits including operational amplifiers. These can fit into one of the electronic industries. These can fit into one or more of the following four principal groups, which I shall call the four C's: C for components, C for communication, C for control or automation, and C for computation. The component companies up to this time were those which came into existence to supply the various types of tubes just described, and others referred to later, as well as the passive circuit elements such as resistors, capacitors, coils, transformers, etc. The second C, communications, refers to the industry built up around AM and FM radio, hi-fi systems, and black and white as well as color TV receivers and transmitters. The third C, introduced the C for control, was making itself evident in what was then referred to as industrial electronics. Industrial electronics may be defined as the use of electronic devices in the control and operation of machines in industry other than in communication computation. The devices for industrial electronics were gaseous diodes and triodes, thyrotrons, pool cathode devices such as mercury arc rectifier, and high voltage and high power tubes. The circuits for this period were power rectifiers, high voltage rectifiers, power amplifiers, high voltage transmitting circuits, induction and dielectric heating, power inverters from DC to AC, measurements, motor control, and the control of industrial process. The computer, the fourth C, had barely made its appearance at this time, and hence the industry is discussed later. The present. The era begins with the invention of the transistor about 30 years ago. Discovery of the bipolar junction transistor. The history of this invention is interesting. History of this invention is interesting. M.J. Kelly, Director of Research and later President of the Bell Laboratories, had the foresight to realize that the telephone system needed electronic switching and better amplifiers. Vacuum tubes were not very reliable, principally because they generated a great deal of heat even when they were not being used, and particularly because filaments burned out and the tubes had to be replaced. In 1945, a solid state physics group was formed. The following quote is from the authorization of work for the group. The research carried out in this case has as its purpose the obtaining of new knowledge that can be used in the development of completely new and improved components and apparatus elements of communication systems. One of the more important specific goals was to try to develop a solid state amplifier. The group consisted of theoretical and experimental physicists, a physical chemist, and electronics engineer, and they collaborated with the metallurgists in the laboratory. The scientists were well aware of the theoretical research on metals and semiconductors already carried out by Bloch, Mott, Schottky, Slater, Sommerfeld, Van Vleck, Wigner, Wilson, and other physicists throughout the world. During an experiment in December 1947, two closely spaced gold wire probes were pressed into the surface of germanium crystal. It was found out that the voltage output with respect to the germanium base at the collector probe was greater than the input to the emitter probe. Brattain and Bardeen immediately recognized that this was the effect they were looking for, and the solid state amplifier in the form of the point contact transistor was born. These first transistors were very bad. They had low gain and low bandwidth and were noisy. Also, the parameters varied widely from device to device. Shockley recognized that the difficulties were with the metallic point contacts. He proposed the junction transistor almost immediately and worked out the theory of its operation. Here was a device that had no pointed wire contacts, and the transistor operation depended on diffusion instead of on the conduction current which was present in a tube. The new devices had charge carriers of both polarities operating simultaneously. They were bipolar devices. The carriers were electrons which are well known and other strange particles which are not well understood. Measurements showed the polarity to be opposite that of the electrons as they were equivalent to positive charges. These particles could only be explained with quantum mechanical theory. They were called holes because they represented places in the crystal where electrons should have been but were missing. The current in a vacuum tube is limited by electronic space charge built up in the vicinity of the thermionic emitter. This space charge, the cloud of electrons, repels any further electrons from being emitted. The phenomenon could not be present in a transistor because the theory predicted that the due device would be essentially neutral except for a thin, immobile space charge layer close to a junction. Hence, very large current densities could be expected from these new devices at low applied potentials. The possibility of obtaining important practical devices without heated elements was immediately recognized. From theoretical consideration, it was known that the transistor could not be built reliably unless ultra-pure signal crystals were available. About 2 years later, T. Bell Labs grew single crystals of germanium and later silicon with much less than one part in a billion of impurity atoms. It was then possible to intentionally introduce controlled impurities called donor or acceptor atoms, the extent of only one part in 100 millions. In this way, they form the junctions of the bipolar transistor. The first ground junction transistors appeared in 1950. The large junction process appeared the next year. 3 short years after the discovery of application in a solid, the transistor was being produced commercially in 1951. The Bell system made a most important corporate decision not to keep these discoveries secret. It actually held symposia to share this knowledge with professors, who could then pass it on to students and even with other companies. It offered to license its patents to any company that was interested in fabricating transistors. The two companies such as Western Electric, which does the manufacturing of the Bell system, RCA, Westinghouse, and General Electric were the first to fabricate transistors, to be followed by many new component companies that saw the tremendous possibilities of this device. By 1952, United States military funds were allotted to transistor research. The armed services was interested in using these devices mainly in missiles, where small size and weight, low power, improved performance, and reliability because of the absence of filament were of primary importance. The investment paid off very well. Solid state companies have actually replaced tubes in almost all military and commercial applications except those involving exceedingly high voltage and power. Most universities in the United States no longer even mention the vacuum tubes in their curricula. Transistor characteristics vary gradually with changes in temperature. For germanium, these variations become excessive for temperatures higher than 75 degrees centigrade, whereas silicon can be used approximately 200 degrees centigrade. In 1954, production of silicon transistor was announced by Texas Instruments. Today, the vast majority of semiconductor transistors and other devices are fabricated from silicon. In 1956, Bardeen, Brattain, and Shockley received the Nobel Prize in Physics. This was the first Nobel Award ever given for the invention of an engineering device, the integrated circuit. Shortly after joining Texas Instruments in 1958, Kilby conceived the monolithic idea, that is, the concept of building an entire circuit out of germanium or silicon. He used the bulk semiconductor to form a resistor. He also fabricated a diffuse layer resistor. He built a capacitor by using an oxide layer for the dielectric of silicon. Also thought of the PN junction capacitor. To demonstrate the feasibility of its concept, he built a phase shift oscillator and then a multivibrator using these resistors, capacitors, and transistors, all made of germanium, with thermally bonded gold connecting wires. However, in the patent application, he indicated the components could be interconnected by laying down conducting material. In 1959, the solid state circuit, later called the integrated circuit, was announced by Kilby at an IRE convention. At about the same time, Noyce, the director of research and development of Factory Semiconductor, now chairman of the board of Intel, also had the monolithic circuit idea for making multiple devices on a single piece of silicon. In order to be able to make integrations between devices part of the manufacturing process and thus reduce weight, size, etc., as well as the cost per active element. He explained how devices could be isolated from one another with back-based PN diodes and how resistors could be fabricated and how connections could be made by operating metal through holes in the oxide to interconnect the circuit components. The idea of using back-to-back diodes for isolation of components was conceived independently and patented in 1959 by Lehovec, the research director of Prague Electric Company. The first modern diffuse transistors were developed by Horney at Fairchild in 1958. He was responsible for the planar process of passivating the emissions, the oxide layer on the surface. He used production physics with big techniques and diffusion process previously developed by Noyce and Moore. The real key to integrated circuit manufacturing was the planar transistor and batch processing. By 1961, both Fairchild and Texas Instruments were producing integrated circuits commercially. Another company soon joined them in IC fabrication. Today, millions of transistors, passive components, and integrations are manufactured simultaneously in one production batch. Field effect transistors. Before the invention of the transistor, a number of people studied the field effect, that is, charge changing conductivity of a solid caused by applied transverse electric field. In fact, the bipolar transistor was discovered, as noted in the foregoing, during these field effect investigations. The Youngstown field effect transistor was proposed by Shockley in 1951. However, early efforts to fabricate this device failed because a stable surface could not be obtained. This difficulty was overcome in the discovery of the planar process, the surface passivation with silicon dioxide, glass, and excellent insulator. A metallic electrode at the gate was placed over this thin 1000 angstrom silicon dioxide layer. A voltage applied between the gate and the bulk silicon induced conductive charges near the surface. The gate extended laterally a few micrometers, referred to as a channel, between two electrodes, the source and the drain, and the current between S and D was controlled by the gate voltage. The first such metal oxide semiconductor field effect transistor was announced by Kahn and Atala of Bell Laboratories in 1960. The reproducibility of these devices was poor. It took about 5 years to trace the difficulty to contaminants, principally sodium ions in the silicon dioxide, and to learn how to eliminate them. Many technological improvements have been made in the basic MOSFET, and this device now rivals the bipolar transistor in importance. Charge coupled device. It is possible to fabricate a long chain of closely spaced gate electrodes between S and D. Charge introduced from S can then be trapped under the first electrode. By applying the proper voltage waveforms, charge can be moved from the first to the second and from the second to the third electrode and so on. This is called charge coupled device. It was invented by Boyle and Smith at Bell Laboratory in 1969. Microelectronics. Reliability, speed of operation, production yields have steadily improved, while cost, power consumption, and size have reduced drastically for both bipolar junction transistor MOSFET integrated circuits. The following approximate dates give some of the idea of the increase in the component transistor, diode, resistor, capacitor count per IC silicon chip. 1951 discrete transistors, 1960 small scale integration less than 100 components per chip, 1966 medium scale integration more than 100 less than 1000 components per chip, 1969 large scale integration more than 1000 less than 10,000 components per chip, 1975 very large scale integration more than 10,000 components per chip. Moore, president of Intel, noted in 1964 when he was director of research at Fairchild that the number of components on a chip had doubled every year since 1959 when the planar transistor was introduced. He predicted correctly this trend would continue. The size of a large silicon IC chip is only about 3 by 5 millimeter area, only about zero point 0.1 millimeter thick, about the thickness of one hair on your head. The chip might contain, in 1978, some 30,000 components, corresponding to 2,000 components per millimeter squared, or about 1 component per mil squared. These numbers are difficult to believe when one first learns of them, particularly since the ICs are manufactured on an industrial plant, not under research conditions in the laboratory. The term microelectronics used to describe such high-density chips, IC chips. They are now commercially available an entire computer on a single chip of the area of which is about 6 to 6 millimeters. The microcomputer is a general-purpose digital processing control system. It indicates what has been attained in microsystems by 1977. In that year, most of the world's $90 billion electronics industry depended on microelectronics. The first IC were digital logic circuits, and these chips were integrated to form combinational systems and sequential systems. Starting in 1964, linear integrated circuits became available, and analog IC systems have flourished. Semiconductor memories. A number of transistor configurations have been devised for storing digital data. These are called random access memories, RAMs. The first LSI RAMs sold commercially in 1970 by Intel and Fairchild. These early RAMs stored approximately 1000 binary bits of information. By 1973, 16,000 bit memories were introduced by Intel and MOSTEC, and 65,000 bit RAMs are expected to be commercially available by 1979. The CCD can be used as a circulating memory, and in 1977, 65,000 bit CCDs were produced. Integrated instruction logic I2L. Until recently, the MaxMet occupied a very small area than the BJT. The latter was much faster than the former. In 1970, the situation changed when Berger and Weidmann at IBM Germany and Harderslow at Philips Netherlands invented a new bipolar transistor logic gate called integrated injection logic I2L. This is not a new device, but rather a new circuit configuration which uses standard BJT fabrication technology. The density of I2L gates has increased to that of MOSFET gates. The speed is high and the power is low. In 1977, Texas Instruments Fairchild Semiconductor introduced I2L chips commercially, and this logic is appearing in digital wristwatches, memories, and microprocessors. Technological improvements are now taking place in MOSFETs, which are increasing the density of a chip and increasing the speed. Hence, it is not evident there will be a clear-cut victory in the I2L over the MOSFET or vice versa. Communication control industries. These industries adopted solid-state electronics slowly at first. Now almost all equipment is transistorized except those involving high voltage or power. For medium or voltage or power, discrete transistors are used. Such application of discrete transistors include power switches for paper punches or tape drive, motor controls, automobile ignition system, TV reflection circuits, inverters, power supplies, and audio and radio frequency output stages. For most of the applications, IC is taken over. The communication industry has changed drastically because of microelectronics. In 1970, the transmission of data constituted a very small fraction of the volume of messages. In 1980, digital transmission accelerated to equal voice analog transmission. Switching and memory in telephone systems are now performed in digital microelectronics. Active voice frequency filters, which are analog, are also implemented with ICs. Obviously, communication satellites became feasible, economically viable because of microelectronics. Similarly, the control industry has been affected drastically by microelectronics. Instrumentation, testing, automation of production process, numerical control of machine tools, energy management are predominantly digital and computer control made possible because of integrated circuits. The computer industry. The most dramatic outgrowth of microelectronic evolution was the creation of the entry-level industry in the computer industry. There has been a great deal of interest in computing machines for over 300 years. For example, in 1633, Picard of Germany described, in correspondence with his friend Kepler, astronomer, a mechanical computer to do addition, subtraction, multiplication, division. He designed a wheel with 10 spokes on it. One spoke of it was longer than the others, and this wheel was placed mechanically next to another similar wheel. After the first wheel made 10 angular increments, which correspond to 10 digits, the large spoke engaged the next wheel and returned one increment. In other words, he invented the carry in arithmetic. About the same time, Pascal, 1642, and Leibniz, 1671, also had similar ideas. But the first really serious effort to build a mechanical calculator had made was made 200 years later, in 1833, by Babbage, a mathematics professor in England. However, the technology simply was not available to convert his ideas into a practicable machine. The first working calculator was electromechanical, not electronic, and it was built by IBM engineers under the direction of Professor Aiken, Harvard, about 100 years later in 1930. It was called the IBM Automatic Sequence Control Calculator Mark I. It was 17 meters long, 3 meters high, and was very clumsy. And it was used to make calculations for over 15 years. The first electronic calculator was built in 1946 by Ecker and Maudsley at the Moore School of Electrical Engineering of the University of Pennsylvania. It was called the ENIAC, acronym for Electronic Numerical Integrated Computer. It was used for computation of ballistic tables for the arms for cylinders, not a general purpose calculator. It contained 18,000 vacuum tubes. It occupied 40 racks of equipment and filled a room that was at least 10 by 13 meters. Also in 1946, IBM built the Type 603, which was the first electronic computer. 2 years later, IBM brought out the 604, which was the last large electronic computer. It built and sold 4,000 of the machines in a period of 12 years. So 1948 was indeed the beginning of the computer industry. Remember that in the same year the transistor was discovered. At this period in time, a number of universities, including Harvard, University of Pennsylvania, MIT, and Princeton, were doing research in computer science and deploying special purpose computers needed by some governmental agencies. The work was funded by various branches of the armed forces, Signal Corps, Ordnance Corps, Office of Naval Research, Bureau of Standards, and the Atomic Energy Commission. Many of our circuit systems and general ideas originated in these universities were used in the commercial general purpose digital computers which followed. 1954, the IBM 650 was built. It's considered the workhorse of the industry at the time. About 1,000 of such machines were sold. This was called the first generation of computers, known as the tube version. In 1959, there appeared the second generation computer, the first transistorized machine. This was the IBM 1790-1794 series. This dominated the computing market for many years. 1965, the third generation machine was built with integrated circuit, the famous IBM System 360. In 1970, IBM introduced the 370 system, which included the first semiconductor memories. In addition to those very expensive 1 million and versatile large machines, the Rosas microelectronics have made possible a flourishing business in small size, medium price, $10,000 mini computers, as well as much smaller, inexpensive $300 microcomputers. Of course, the reader is familiar with the handheld calculator which does multiplication, division, addition, and subtraction and sells for only a few dollars. The import of microelectronics was dramatically expressed in noise in the following 1977 quote. Today's microcomputer, at a cost of perhaps $300, has more computing capacity than the first large electronic computer ENIAC. It is 20 times faster, has a larger memory, is thousands of times more reliable, consumes the power of a light bulb rather than a locomotive, occupies 1 by 30,000 times the volume, and costs 1 by 10,000 as much. It is available by mail order or from your local hobby shop. Remember that the microcomputer is built on a silicon chip whose area is less than 1 by 4 or 1 by 4 inch. Cochrane and Boone of Texas applied for a patent for the microcomputer in 1900. It was granted in 1978. The future. The foregoing completes the history of electronics and electronic industries up to 1978. This is already a start towards the merging of the computer and communication industries, which might be called information manipulation. This includes storage of information, sorting, computation, information retrieval, transmission of data. Combination of computer communication will penetrate many disciplines. Applications made in the fields of law, medicine, biological sciences, engineering, library services, publishing, banking, information system, management control, education, and defense. Microelectronic applications to the automobile, electronic ignition systems, emission control, safety systems, improvement of efficiency, video games to the home, systems of energy conservation, control application, smart burglar alarms, the personal computer, and so forth, to medical equipment, to federal electronics, will expand tremendously. I believe that silicon technology and the devices which result therefore will dominate electronics for at least the next decade. Restriction between a device, a circuit, a system will become more and more blurred. Furthermore, the principal electronic industries will continue to be the forces, components, communication, computation, and control. These will become exceedingly difficult to recognize as separate industries because they will overlap more and more. Total electronic equipment consumption in 1978 is equal to 66 billion in the United States and 107 billion worldwide. This is the history of electronics. I hope you enjoyed it. Thank you.